Assalamualaikum warahmatullahi wabarakatuh. For group project M80-575, we are from group number 2 and we are going to present about curve fitting and numerical integration analysis of Tasik section 7 using Gauss elimination.
Hello, today we are here at our Tasik, Seksyen 7 Syarah. We are here to calculate the perimeter of this Tasik for our assignment MAT 575.
For the problem statement, the boundary curve of Tasik section 7 cannot be represented using a non-mathematical equation because the lake has an irregular natural shape. Instead of having a continuous equation, we only obtain several discrete coordinate points from the graph paper map. To simplify the analysis, the lake boundary was divided into 4 quadrants. The actual curve length of the lake is known to be 1.67 kilometers. Therefore, numerical methods were needed to model the boundary curve for each quadrant. In this project, we use Gauss elimination to determine the quadratic equations and numerical integration to approximate the arc length. Finally, we evaluated the accuracy of our approximation by comparing it with the actual curve length.
Thank you, Nylam, for explaining the problem statement. Now we will move on to the objective of our project for Tasik section 7. The first objective is lake boundary modeling. We need to trace the irregular shape of Tasik section 7 from the Strava path onto the graph paper. And then we will divide it into 4 quadrants using a piecewise quadratic regression model. The equation is y equals to a0 plus a1x plus a2x squared. The piecewise function, which means a simply methods that change depending on the equation input. Instead of using one single equation for everything, it will use a different formulas for different pieces so that we will easier to get the calculation for each country.
Second, to construct a robust 3x4 matrix using the discrete xy coordinate extracted from our graph paper plot. This matrix represents the system of linear normal equations required for quadratic regression, which then resolved systematically using the Gauss elimination method.
For the third objective, we quantified the geometry of Tasik section 7 using Gauss elimination and definite calculus integration. First, we selected several xy coordinates from each quadrant of the lake boundary. This point we substitute into a quadratic equation, that is to find the area under the curve and the arc length. This objective shows how Gauss elimination and calculus can be applied to analyze irregular real-world shapes mathematically.
As shown on the graph, the Strava path was traced based on its coordinate, dividing the shoreline into 4 distinct piecewise segments with 12 marked boundary points. From this plot, distance between the points were analyzed using two methods. I calculated distance x bar using the standard distance formula and the measured distance x obtained physically by tracing a thread along the actual curve boundary.
For quadrant 1, we use Gauss elimination to solve for the quadratic function. First, I collected the coordinates and set up the normal equations in metric form. Then, I performed forward elimination to obtain an upper triangular matrix, followed by back substitution to determine the values of a0, a1 and a2. The quadratic function I obtained is fx equal to negative 87.18 plus 42.91x and minus 4.575x squared. Using this function, I calculated the arc length as 6.335 centimeter using a numerical integration.
For quadrant 2, the analysis covers the interval from x equal to 5 to 10.4. First, we do the metric elimination. Metric built from the data table, reduced into an upper triangular form to clear out the values below the diagonal. Next, do the back substitution. Solving the rule from bottom to top, stable coefficient, establish the final curve formula, then the fx will get the negative 7.68. 18 plus 5.9966x minus 0.3490 x squared. Then calculate the arc length and the area.
Now I will explain quadrant 3, which is my part, and how we use Gauss's elimination to solve for the coefficient. The first step in order to solve for the quadrants, we will collect coordinate points from the tables that we use on the graph paper for quadrant 3, and then we will calculate the sums needed for the normal equation, including the total of x, y, x squared, x power of 3, x power of 4, x multiple y, and the total of x squared multiple y. The second step is we will set up the normal equation in 3 times 3 augmented matrix. And the third step is we will apply the Gauss's elimination method, and we perform forward elimination to get zeros below the diagonal. It will convert the matrix into upper triangular form. The fourth step is we will use the back substitution to solve for the coefficient. As a result, we will find the A2 first from the bottom row, since it was easier to get the values. And then we will substitute the value from A2 into the row above to find A1, and lastly finally found A0 from the top row. And lastly, we will get the quadratic function obtained for the quadrant 3 is fx equals to 668.432 minus 112.641x plus 4.805 x squared. Next, the interval for quadrant 3 we will get from the x coordinate from tables, which for quadrant 3 range from coordinate 7 until coordinate 10. The first is x equals to 10.4 to x equals to 11. And the Gauss's elimination was chosen because it is systematic and efficient for solving 3 times 3 systems.
For quadrant 4, from the coordinate that we have been plotted into our graph, we substitute them into the quadratic equation. That is y equals to a0 plus a1x plus a2x squared. Next, we form augmented matrix and solve it using the Gauss elimination method. During forward elimination, we simplified the matrix into upper triangular form. Then using back substitution, we obtain from the equation, that is a0 equals to 36.93, a1 equals to negative 5.6333, and a2 equals to negative 0.375. So the quadratic equation for quadrant 4 is y equals to 36.93 minus 5.633x plus 0.375x squared. After obtaining the equation, we calculate the arc length and the area under the curve using definite integration. The arc length obtained was approximately 7.749 cm, while the area under the curve was approximately 15.412 cm square. This result represents the boundary lengths and the area contribution of quadrant 4 for Tasik Seksyen 7.
Therefore, this is the summary of the calculation of every quadrant, and we will get the quadratic function, which is the fx equation. The first quadrant is the fx1, the second quadrant is the fx2, The third quadrant is the fx3, and the last quadrant, which is quadrant 4, is the fx4. Next, after we have got the fx equation, we will calculate the arc length to get the total of the distance in each quadrant. And after we have total up the arc length, we will get the approximate value of 28.47 cm.
The area that we found using Gauss elimination method is 5.38, and the relative area is 0.1589, and the percentage relative area is 15.89%.
Next is discussion and conclusion. Manual measure and limitation. Manual measurement of the coordinates from graph paper may introduce small human errors during plotting and reading. In addition, the size of the printed graph may not remain constant, as it can become slightly bigger or smaller during the printing process. This affects the scale and accuracy of the coordinates measurement, which can contribute to errors in the calculation. Besides that, the quadratic model used may not perfectly fit the actual irregular shape of the lake boundary, since natural curves are more complex than smooth mathematical equations. These factors contribute to the difference between the approximated and actual arc length values.
Besides, the second discussion is the method insight. I will explain more for the first bullet point, which is the lake changes curvature direction, which means when we solve for the quadratic coefficients in each quadrant using Gauss's elimination method, we notice a clear pattern in the value of A2. In quadrant 1st and 2nd, A2 was negative. In quadrant 3 and 4, it flipped to positive. This tells us that the lake bends downward on the first half, which is the quadrant 1st and 2nd, and bends upward on the second half, which is the quadrant 3 and 4. Without using Gauss's elimination separately on each quadrant, the structure curvature pattern would not have been visible. Another thing we observed was during the back substitution step, which means clean fractions in all 4 quadrants prove consistent coordinates and error-free calculation. For all 4 quadrants for 1, 2, 3, and 4, the results came out as clean, simple numbers without messy decimals, which means it only have 1 decimal points in the graph paper. This tells us 2 things without us having to double check everything. First, our coordinate readings from the graph paper were consistent across all quadrants. Second, we made no arithmetic mistakes during forward elimination or back substitution. If we had made an error, the numbers would have immediately turned into irregular decimals.
Moving forward from the discussion point, the conclusion begins with efficient curve fitting. By implementing the Gauss elimination method, resolve the system metric, the raw coordinate data was successfully transformed into precise mathematical model for each quadrant.
What we can get from this assignment is we can gain practical engineering application. This project demonstrates how engineering mathematics can be applied in real-life situations by using numerical methods such as quadratic regression, Gauss elimination, and calculus integration. We were able to model the irregular shape of Tasik Seksyen 7 mathematically. The data collected from the graph was converted into equation, which allowed us to calculate the area and boundary length of the lake more accurately. This shows how engineers use mathematical modeling and numerical analysis to solve practical problems involving irregular structures and physical topography. Overall, this assignment helped us understand the importance of mathematics in engineering application, especially in data analysis, measurement, and problem solving.